Welcome to my presentation for the ECG 772 project. Title of my paper is Analysis of Motor-Driven Cart on Track, Nonlinear Extension to Linear Dynamics and Controls. So quick table of contents, basically everything I've covered: introduction, background, modeling, control, simulation, experiment, results, conclusion, and my references. This is a quick introduction. So the figure shows a motor-driven cart coupled with pulley and belt. This is a basic setup for both the model and the experiment, as you'll see later. So motor and cart dynamics are pretty well understood, and they're pretty common in literature. You see them a lot in textbook examples. These dynamics can be further applied to more complex systems. For example, inverted pendulum on a cart, or even double and triple inverted pendulum on a cart. Linear models are easier to implement, but may not be completely sufficient, so you have non-linearities that'll cause error in practical considerations. These can be friction, limit cycles caused by friction, or some other wanted effect that could reduce the accuracy of the model. So for this paper, both the linear and the non-linear motor cart model will be explored just for comparison, and so we'll take a look at both and see what the differences are. When doing the background research for this paper, I noticed inverted pendulum on a cart is commonly seen in literature and may be considered a benchmark in controls research. You see this a lot. A lot of new control laws are applied to inverted pendulum models, and they're kind of used as a reference. Solomon explores a dynamic model for a two-axis belt-driven position system where an improved nonlinear model is developed. Aside from friction, he adds things like belt dynamics, which include the stretching and the contraction of the belt, and other nonlinearities, which come up with a pretty accurate and interesting system. Hayes from 3 introduces an improved sliding mode controller in a motor conveyor mass model. The figure on the left shows a linear sliding cart model. You can see the force applied, and the resistance to motion is the D'Alembert force of acceleration and the viscous friction force. On the right is a linear electrical motor dynamics model. We have the resistance R, inductance L, the back EMF, and the current flowing through the system with the applied voltage. It doesn't include the inertia terms, but that's going to be coupled with the motor. For the linear model, the classical linear model for the cart and for a DC motor can be seen in the last figure. The differential equations for the cart can be summed up as follows: mx double dot plus bx dot equals f. M is the mass of the cart, B is the viscous damping coefficient, and F is the driving force. The dynamics for the motor are Li dot plus Ri equals V minus Km theta dot. Since we're looking at the displacement in the x direction, we want theta dot equal to x dot over R. L is the inductance on the motor, R is a motor resistance, I is a current, V is applied voltage, and Km is a motor torque constant, and theta dot is a motor angular velocity. The torque constant can be obtained experimentally or sometimes from the motor data sheets. The applied force on the motor will come from the torque produced by the motor. Tau equals Kmi. Since F times R equals torque, where R is a pulley radius, the combined motor cart dynamics along with 2 become mx double dot plus bx dot equals kmi over r. At this point, equation 3 can be solved for in terms of I and I dot and be substituted into 2. In state space form, x1 equals x, the position, x2 equals x dot, the velocity, and x3 equals x double dot, which is the acceleration. x1 dot equals x2, x2 dot equals x3, and x3 dot is equal to the dynamics. So for the nonlinear model, the complexity of the nonlinear model will depend on external requirements such as the computational limits, output accuracy, time, cost, etc. You can make it as complicated as you want, but if we don't need it to be that complex, then there's no reason to. The main nonlinearity in the experiment is a Coulomb friction and the saturation in the input. Other mechanical nonlinearities can include belt stretch dynamics or additional inertia terms coming from the gearbox or the pulleys and other types of friction. Electrical nonlinearities can include any nonlinearities in the motor, perhaps a resistance, maybe they're a function of temperature, and also anything in the controller as well. For Coulomb friction, we could represent it with the signum function. So the signum of x dot is equal to kd if x dot is greater than 0, minus kd if x dot is less than 0, and 0 if x dot equals 0. So it's a constant term whenever there's velocity present, otherwise it's 0. The saturation function, saturation of u, is phi if u is greater than phi, minus phi if u is less than minus phi, and u if the absolute value of u is less than phi. So essentially, u remains itself until you hit the limits given by phi and minus phi. Those are the saturation limits on the input voltage. And kd is the Coulomb friction force. And it can be shown that the derivative of the signum function is twice the direct delta function, or 2 times the impulse function. This is going to show up in the differential equations for the nonlinear model. So similar to the linear model, the system of equation becomes x1 dot equals x2, x2 dot equals x3, and x3 dot equals the dynamics. So for the controls, we have both linear controls and nonlinear controls. For linear controls, a proportional feedback controller was chosen for trajectory tracking. The input or the voltage into the motor is V equals U, where U equals Kp times X minus XD, or Kp times the error. Kp is a gain and XD is a desired trajectory over time. In this case, we're choosing XD to be some sort of sinusoid. The benefit of this controller is that it can be easily implemented and only requires measurement of the cart's position. There's only a single gain value that needs to be tuned, Kp, so it makes operation much simpler. For the nonlinear controls, we're going to go with feedback linearization. The input U is chosen so as to cancel the nonlinearities while introducing a full state feedback. Based on the nonlinear dynamics from 12, U is equal to nu plus all the other nonlinear terms. So K1, K2, and K3 are constants, and they're chosen so that the linear dynamics resulting from equation 14 go to 0 or close to 0 as time goes to infinity. For the simulation, I chose a linear model with proportional control, a nonlinear model with proportional control, and a nonlinear model with feedback linearization. For the linear model with proportional control, the parameters for this is Kp equals 200. I also included an integral term, but it's pretty low and it doesn't really have an effect in the system. I used it on the experiment, so I kept it for the simulations as well. So Ki equals 1, amplitude is 0.15 meters, period equals 10 seconds. As you can notice, I have the upper and lower limits on the voltage, but since this is a linear model, it's not being affected. You can see in the transients, the initial voltage exceeds the 12 volts. Otherwise, we have pretty good tracking, and as expected, there's a steady state error. For the nonlinear model with proportional control, the parameters are the same. Kp is 200, Ki is 1, amplitude is 0.15, t equals 10 seconds. The biggest difference is we do have the saturation on the input and the very nonlinear nature on the input. For the output, you can see these flat peaks, flat top peaks that are due to the Coulomb friction. So basically, when the motor input is too low, the cart will stop moving due to friction. This is something that is seen more in the experiment, is not seen in the linear model. So it's important that we're capturing this in the nonlinear model. So with feedback linearization, so you can see that the tracking is much better than both the linear and the nonlinear model. You lose all the flat top peaks that you see in the nonlinear model with proportional control. And you can see that the input, although it does get saturated, it's also very high non-linear. But overall, the tracking is really good after a small initial transient. For the experiment, the figure shows a basic experimental setup. So the track consists of a 600mm linear rail, 3D printed cart, and 3D printed brackets as well. A cogs belt, a 12-volt 550 RPM motor. The controller is an Arduino Uno along with a PWM motor driver with an H-bridge. The sensor is an optical rotary encoder with 1200 counts per revolution. The Arduino Uno processes the encoder signal and calculates the output that goes to the motor driver via PWM signal. The motor driver amplifies the PWM signal and the H-bridge controls the motor direction. So for the results, the linear model fails to capture the majority of the experimental results, such as the ones discussed above. As expected, the nonlinear friction caused unwanted effects on the output, specifically those flat top peaks. The nonlinear model with proportional control captures many of the nonlinear effects found in the experimental model. It tends to be a much better model, and it matches the data pretty well. In the nonlinear model with feedback linearization, the input voltage signal does not match the experimental input. We'll see that in a bit, but that was the only difference with the model and the actual experiment, is that the voltage input didn't really look like how it was shown in the model. It probably could have been due to noise or maybe some other dynamics not included. And the tracking error in the experiment is not as small as it shows in the model, but it's still significantly better than the proportional control model. So for the first proportional control experiment, we have parameters Kp equals 200, Ki equals 0, A equals 0.15, and T equals 2. And you could see the saturation on the input once it goes past 12 volts, and this kind of causes a weird shape in the sinusoid. It's a little bit more triangular, and you do get a lot of error. If you compare this with the model, the nonlinear model, it actually looks pretty similar. Once again, parameters are 200 for Kp, Ki equals 0, A equals 0.15, period equals 4. There is a little bit of saturation in the start on the input, but otherwise you get decent tracking until you hit those flat tops as predicted by the nonlinear model. Another experiment, experiment 3, with values Kp equals 70, Ki equals 0, A equals 0.15, and T equals 1. So the period is quite small, and you can see that the inertia and the motor dynamics can't really keep up with the amplitude of it. So you get some amplitude loss, and the error is quite high. But it does show that there's no truncation because the velocity tends to be pretty high throughout the whole sinusoid. And experiment 4, this one has a PI control. These are the ones shown in the simulation results. The Kp equals 200, Ki equals 1, A equals 0.15, and period equals 10 seconds. And if you look at the nonlinear model in the simulation results, you get the same flat top peaks, and you get some steady state error as predicted. And you could look at the input voltage. It looks similar to what is predicted by the nonlinear model. Next, we apply feedback linearization to the experiment. This is experiment 1 with the following gains shown below. The period is 10 seconds, and what I noticed from the experiment is that the larger the period, the poorer the tracking, especially during the peaks. You get a lot of flat tops. And with the feedback linearization, even though the period was 10 seconds, the overall tracking was very well. As you can see, the voltage input is quite erratic, it's very noisy, and it doesn't really catch what the model predicted. Same with experiment 2. The only difference is that the period is 4 seconds, so it's a much smaller period. But you can see that the overall tracking is pretty well, and it's much better than the proportional controller. And you can see the noisy effects of the input voltage, which once again is different from what the model predicted. In conclusion, accounting for nonlinear effects in modeling can provide better insight into the system response. This can be beneficial if the system may become unstable or reach an unwanted limit cycle, as is common with nonlinear friction. If the linear approximation is unacceptable, feedback linearization can be performed on the nonlinear system via various techniques shown in the textbook. Future work would be to look at other nonlinear controls such as sliding mode and adaptive control. And here are the listed references 1 through 4, and we have references 5 through 8. So this has been my presentation. Thank you very much.